Hello and welcome to another episode of Ether Cosmology, Ether Roundtable. We're going to be getting into Toby's presentation on relative motion in geophysics. All right, Toby, give you a soft intro or whatever. Whenever you're ready, sir.
Excellent. I'm also live now as well over on Ether Cosmology. If you're joining on Ether Cosmology or Space Audits, thank you for tuning in. If you didn't know, last Saturday or this previous Saturday, me and Alan were in a debate over on Modern Day Debate, and I gave my intro. We had originally 6 minutes to do our intros. We pushed them and got 8, and then I still had way too much for 8 minutes, so I had to rush through it really fast and still didn't get through it all. So we decided today I will just go through it all without having to rush, uninterrupted. And then after we go through this, me and Alan are going to touch on a few things that came up during the debate that we just want to provide some extra context and clarity on. And then we're just going to have open discussion. So, yeah, thanks for being here. And yeah, anything else that we want to say or do before I get into this that you can think of, Alan?
Nope, that's it.
Cool. All right. So, we're going to talk about three globe claims. They have their claim of motion,
Oh, can you screen share?
curvature. Oh, I'm not screen sharing on Discord. I knew I forgot something. My bad. There we go. All right, you can see now, right?
Mhm.
Excellent. So, motion, curvature, geophysics. We will start with motion, and I'm going to read this quote here from Ruyang Wang. Wait, is this the one that I want? No, this is the old version. My bad. I have the wrong presentation open.
Someone's saying that the sound is.
Out of it
One
because
second.
it's a bit more concise. The heck? There we go. So yeah, just bear with me one moment if you're listening in. I apologize. Go ahead and so this is the first one. Okay, well, pardon the typo there. Let's just go ahead and get into it. So, three globe claims, motion, curvature, geophysics. We will start. But before we get into that,
Live stream
let's talk
ended.
about what's that?
Your stream
Oh,
ended on Discord.
dude, I am just like can't do this today, huh? Thanks for bearing with me. Can you see that?
Sir.
Oh, I shared the wrong one. Here we go. All right. Now we're good. So let's talk about the paradoxes. If you believe in the globe, these are the paradoxes you have absorbed as your position. You've got the particle wave duality, you've got the twin paradox, Ehrenfest paradox, Einstein-Podolsky-Rosen paradox, Schrodinger's cat, Heisenberg uncertainty, Newman-Selinger gravitational paradox, the information paradox, a violation of Newton's shell theorem, and a violation of maximum momentum, minimum energy rotation, also a violation of curved visual space. In addition to that, many more. So we will start by talking about motion. And as we all know, we feel no motion. All flight on Earth utilizes a stationary baseline. That includes planes, missiles, helicopters. Here's a document from showing commercial flight simulation and how that works. And it says the flight area is the space above the ground level where the rotation of the Earth and the curvy motion of mass center of Earth are neglected. And then here's dynamic positioning equations of motion. This uses a non-rotating Earth. Here's helicopter equations of motion. This uses a flat, non-rotating Earth. So question, if pilots have to treat the Earth as stationary and we can't perceive any motion, is there any way we can measure it? Answer is yes. We can use the induction rate of light. We can measure absolute velocity as understood since at least 1818. That goes back to Fresnel, to Fresnel when he first derived his math for the Fresnel drag. And in 1865, J.C. Maxwell made it very specific because he used Faraday's experiments and he used the known values of the electric constant and the known value of the magnetic constant in his electromagnetic wave equations. And he used that to show that light behaves as an electromagnetic wave, and that requires a substantive medium, aka the ether. And if you go through and look through J.C. Maxwell's his book where he first derived this math, all his work when he first derived these equations, he repeatedly invokes the ether. And Faraday, who did all the experiments that provided with Maxwell with his knowledge to derive these equations, even Faraday understood the idea of lines of force and lines of motion. These people understood that there was something that connected free space and that there was an idea of absolute space. So that's why in 1887, when they want to do what's called the Michelson-Morley experiment, they knew exactly what they were doing. And the goal of the Michelson-Morley experiment in 1887 was to use what's called interferometry to measure absolute motion using what's called, the speed of light, quote unquote. And so just a quick rundown. Basically, you have a laser that gets shot out here or a wave of light, and then this splitter will let it go down this way and then this way, and then they'll come back and recombine and go to the detector. And then because you have so basically the wave gets split in two, and when this one goes out and comes back, and this one goes out and comes back, and they recombine, if there's a speed difference or the time difference in the amount of time it took for this to come back and this to come back, when they recombine, they'll either be in phase with each other or they won't. And then you can look at what's called the fringe shift, which is what these are. These are classic fringe shifts from early experiments, and you can use that to then use math to derive the how fast each wave of light was going and what the difference was between this way, essentially. And so they use that to detect the absolute motion of the Earth. And it should have measured what they were going to do was measure the orbital motion of the Earth around the sun. So don't confuse that with the rotational motion. This was supposed to be the orbital motion that they measured. And that was based on a premise of a substantive medium, which is necessary for electromagnetic waves propagation. And they used essentially the speed of light as their dependent variable. And then their independent variable would have been the direction that the interferometer was pointing. So as you would change that orthogonal vector, the two orthogonal vectors of the two different waves of light, and you rotate that thing around slowly, you would then observe the fringe shift changing and morphing as you turned it, and you could tell if light was going faster or slower in those different directions. And when they did that, the result was not equal to the Copernican principle. They didn't detect any orbital motion. They did get a small fringe shift, so they did detect a little bit of something. Uh, and that result that they did detect can be explained with a stationary Earth and an ether wind. But what they said was that they detected nothing. They called it null. And so if we measure something to see if it's moving and we don't get any measurement, it's not moving, right? Well, not really, because in 1905, or at least that's what they tell us, because in 1905, Albert Einstein stepped in with his On the Electrodynamics of Moving Bodies, and he said, there's no ether. We have a one-way speed of light that is always the same, no matter what. And you're not allowed to invoke absolute space or absolute time. And just be really clear here. This is the paper. This is like the first paragraph of the paper or second. And the he's saying examples of the sort together with the unsuccessful attempts to discover any motion of the earth relatively to the light medium. So what are you going to do? Well, he's just going to call the whole light medium superfluous. He says the introduction of a luminiferous ether, which would be the light medium, will prove to be superfluous in as much as the view here to be developed. So the view here to be developed. So it will not require an absolutely stationary space provided with special properties, nor assign a velocity vector to a point of the empty space in which electromagnetic processes take place. And this is kind of, I know it's maybe sounds a little dense, but it's really crucial because I won't get too into the weeds on that yet. Maybe we'll get into it in a bit, but let's just keep moving here. Let's keep moving forward. Uh, so we saw here, he talked about they couldn't detect any motion of the Earth. This is him deriving special relativity. And he says he invokes imaginary physical experiments. And then he says, so he's invoked no motion of the Earth and imaginary physical experiments. And then he says, in agreement with experience. So the experience he's invoking is imaginary physical experiments and no motion of the Earth. He says we further assume the quantity, a universal constant, the velocity of light in empty space. And then here's him showing that no matter how close you are to the speed of light, even if you are zero point 0.9 speed of light, and then you were to add zero point 0.9 speed of light than that to that, you would still be less than the speed of light. You cannot surpass the speed of light. Kind of like telling you that 2 plus 2 does not equal 4. And he's showing here it follows from this equation that from a composition of two velocities, which are less than c, there always results a velocity less than c. And then he says here the velocity of light c cannot be altered by composition with a velocity then less than that of light. So no matter what, as you get closer and closer to light, you will never quite catch up that speed. Even if you were the speed of light already and you were propelled forward in an inertial frame, they can't even acknowledge the additional velocity from your inertial frame because uh, what's that? Sorry, I thought I heard someone. Uh, but yeah, so moving on. So they said speed of light has to be constant. That's how we can have the Earth not be in motion. That's the best way to explain that for them if they want to have have the Earth be in motion. But then in 1913, Georges Sagnac came along, a Frenchman, and he took an interferometer and he spun it. And what he found is that the velocity of the spin
Yo, one
is
sec.
actually
Yo,
okay.
Orwellian, I muted you for a second. You're hot micing. I don't know if you
Cool,
know or
cool,
not. Yeah.
Trying to figure it out right.
Yep, no
cool.
worries.
But yeah, so he showed right then and there when he did his interferometer rotation that the speed of light is relevant to the inertial frame and that violates special relativity. And that if you think about it, right? So what they're able to measure is this difference right here, and because of the speed that changed. And if you think about it, this is exactly like orbital motion. This is the same thing. You're measuring that translation of speed, but they essentially they came up with what's called they Lorentz transformed this eventually. The explanation for this is difficult for the observer, but they can mathematically explain it. Anyways, in the 1920s, so we talked about how in Michelson-Morley there was a tiny bit of a fringe shift that the interferometer picked up. And in the 1920s, Dayton Miller was very interested in that. So he took the exact same design of interferometer and started playing with it and built upon it. He did a ton of experiments and he found he instead of just doing it one time and then, throwing his hands up, he started doing it over and over and over again and did it over periods of time. And he found that not only is there that okay, so they said that there was a null result and the tiny bit of result that they got was they called it instrumental error. Well, what Dayton Miller found was that the instrumental error keeps going the same direction, which is kind of crazy. Like, why would you have this different interferometers all keep showing the same instrumental error direction? That's clearly something else is going on. And not only that, but as the time of the year progressed, or actually, we'll say the time of the day, first of all, throughout the day, that ether flow is what we call it, the preferred directionality of the speed of light, the fact that it goes faster one way than the other, that actually matches the motion of the sky. So you have a periodicity to the day. Throughout the day, the speed of light goes faster and slower in one direction than the other with the sky. And then it also has a periodicity that goes with the whole year. So as the seasons progress and the sun is moving on its analemma, that's measured in the interferometer. Uh, and then on top of that, the measurement that they get of that preferred directionality of the speed of light and the fact that it goes faster one way than the other, it's greater at altitude. So the higher that you go on the Earth, the more of that effect that you measure. And it's in relation to the motion of the solar system. So it's the way they would say it's how we're going around the sun, but that's measured as what they will get to it. They call it rotational motion, but um they say that's us going around the sun, but it's really just what the sun's doing in the sky. But so that's what Dayton Miller measured in the 1920s. But they ended up smearing him. They wrote off all of his work. They're still to this day writing papers to write off his work. And so in 1925, just to kind of bring this all together, Michelson Gill Pearson came along, or the Michelson Gill Pearson experiment took place. And at that point, they claimed to have measured the rotation of the Earth. So just to make it real clear, Michelson Morley, they want to measure the orbit. They use an interferometer. They didn't measure any orbital motion. They got a little bit of a fringe shift. They said that's just an instrumental error. Then in 1925, they measured the exact same thing. And they said it was Earth rotation. And they claim that they were able to measure that because Earth, because it can only, interferometry can only measure rotational motion. And linear motion is undetectable. Closed loop rotational motion is detectable according to them. And so you would think, well, isn't the orbit of the Earth around the sun a rotational vector? Isn't that moving in essentially a circle or an elliptical in a closed loop? Wouldn't we just be able to measure that anyways? Well, they say no because Einstein said that it's actually we're actually moving through a linear geodesic, and that's why we can't measure anything with interferometry. So this is the claim: you can't measure rotational motion with interferometry, yeah, linear motion. You can only measure rotational motion with interferometry, not linear motion. That's their claim. But so, anyways, jumping forward a great deal here. There's obviously a lot more that happened within those years, but jumping up to 2001, we have Yuri Galev with his own experimentation. This is the paper, Ethereal Wind and Experience of Millimetric Radio Waves Propagation. And what he found is that the speed, she's talking about the ether wind that we were just discussing. And he's talking about how that speed is been measured, does not contradict the hypothesis. Essentially, he goes through and he corroborates Miller. So this is him. He did his own analysis of Miller's measurements. And he says the suspected ethereal wind speed at the altitude 265 meters above the sea level in Cleveland has the value about 3 kilometers per second. And at 1830 meters, the observatory in Mount Wilson, Pasadena, is about 10 kilometers per second. So you have a massive fluctuation there. And if that's the case, then you can't say it's a rotational vector because the rotation can't get faster and slower as you go up and down because it's purely supposed to be measuring rotation of the Earth. So the rotation doesn't go any faster or slower as you move outward from the radius. Now, your linear motion would, but your rotational motion wouldn't. So yeah. And this is Galev's work. And he took it all. He took what Miller did and put that in here at Miller's altitudes. And then this is his own work, his own altitudes, or sorry, right here. This was his work as well. Yeah. So this was all his work. And he corroborated exactly what Miller claimed. And then in 2004, so now we know it gets greater at altitude, which already is enough to throw the whole thing out. Like it's not a rotational vector. But just to really drive the nail into the coffin, in 2004, Ruyang Wang released or published Generalized Sagnac Effect and also Yi Zhang and Aipeng Yao. And this is a quote from PhD Robert Bennett, from a landmark experiment. He called it a landmark experiment, the linear Sagnac test of Ruyang Wang. Belief that the Sagnac test of 1913 only applied to rotational motion was discounted when Ruyang Wang found the same results for linear motion in 2004. The Sagnac result has never been credibly explained, despite its wide application in modern technology. In turn, the Wang paper has been virtually ignored in the last 10 years. Analysis of Wang's result in the conveyor lab frames with the premise of ether drag logically leads to identification of preferred motion in an absolute frame of reference. That's called reality. The earth-bound laboratory frame, reality. Because essentially, you have to step out of reality in order to acknowledge the way that they explain these things. These things are not the constancy of the speed of light was violated by Sagnac in 1913, and then it's violated again with the generalized Sagnac effect in 2004, as well as many other Sagnac experiments. But so it's crazy because let's just talk about this real quick before I go into their rebuttal. But so this is what Ruyang Wang did. So you have a fiber optic gyro right here. And remember earlier we talked about the interferometer. This is not that different from the interferometer. It's the same concept essentially, except they have some qualms. They say because it's a closed loop that somehow matters. But basically you have a fiber optic gyro here, and you've got an emitter and a detector in here. And you're doing the same thing where you're splitting a light wave. And then as it goes out, you have the light waves going out this way and this way, opposite directions. They're So they send the light waves out, and then they're coming back into the detector here. And then as they're doing that, they do this motion. This moves this way, this moves this way, and this moves this way. All one jutting motion, right? And as that happens, see all these V's? These are velocities. These are velocity vectors. And every single one of these three here, these get measured in the fringe shift. So according to them, only closed loop rotational vectors should be getting picked up. So just these wheels. That's all we should be getting picked up. But that's not what Wang found. So I had to take a lot of the math out because I didn't want to spend too much time on it during the presentation. But Wang showed that it's essentially the Sagnac effect of rotation. It has a special case for linear motion. And he even says here, hey, look, we could do a fiber optic sensor for measuring linear motion with nanoscale sensitivity. That means like a speedometer. Like you could put this thing in your car, know exactly how fast you're going without even having to know how many times your wheels turn. Because if you don't know, that's how your car knows how fast it's going. And every one of these, every device that we have essentially that calculates speed has a problem of needing to have an external reference frame. That's like even airplanes that have to rely on GPS. You can extrapolate things from the magnetic field in the sky, but in order to actually know for sure how far you have traveled, you have to use some kind of external reference frame. So, in like the car with the wheels, that would be the ground that you're using. And then in this case, it would be the background medium, aka the ether, which they cannot acknowledge. And also, if this is real, then we should have measured orbital motion of the Earth in 1887, even if we grant them Einstein's magical linear geodesic. So this is another one that he did. And so in this one, this part's not even moving. This is slack, and they have their source and their detector, and just this portion here moves that way. So there's not even a rotation happening, just that one motion. And that one motion gets picked up directly proportionally to velocity, not acceleration, directly proportional velocity in the detector. And I'm sorry if it's a little bit in the weeds here, but this is something that, people will, this gets deep because, this is talking about relative motion, and this gets really convoluted because of the way that they've ad hoc'd in explanations on top of explanations on top of explanations, which hopefully that's becoming clear by the fact that, George S. Sagnac should have thrown this whole thing out the window in 1913, but they got away with excuses. And then now they're still getting away with excuses even after Ruyong Wang did this. And so one thing about this to note is that he did this once in 2003. He generalized it he had generalized it in 2003. And the Naval Research Laboratory loaned him his very expensive fiber optic gyro to do that. And then they loaned it. And then, so he did that. He filed the provisional application for this patent for a standalone speedometer using two spaced laser beams, which can only work if it detects linear motion. And then again, later in 2004, he did this experiment, got another fiber optic gyro loaned to him from the Naval Research Laboratory. And, and it was in full agreement with his first experiment, full agreement with basically all of his hypotheses. The dude was brilliant. The dude is brilliant. He understood GPS very well. And that's what led him to even explore this topic, was just looking at how GPS worked, because GPS on its face refutes all of this. And I guess I had taken that out of here, but I was going to talk a bit about Wang and Hatch, just going into detail about GPS, because I'll just really quick touch on that. And that's, if you start looking into geocentrism or flat Earth or anything like that, one of the things people have to try, if someone's going to contest, or let's say defend the globe, they're going to defend the Einsteinian paradigm and heliocentrism, the spinning space ball. In modern times, you can only do that with Einstein. The whole thing is built upon an Einsteinian framework. And that's this idea of the constancy of the speed of light. I know it seems crazy that I've got a hound on this so much, but that's because so much is wrapped up on this crazy concept of a constant speed of light. Well, the thing is, you just look at how GPS works. I was told when I started looking into this, oh, relativity is real. You just don't know about GPS. Just go look at GPS, Flurf. Go look for your go be proven wrong because GPS is proof of relativity, they tell you. Well, when you actually go and look at it, I mean, there's like, so Ron Hatch, extremely well credentialed within the world of GPS. He ran, what was it, the Institute of Navigation, or he was the head chair of it. He started Navcom Technologies. He was a GPS consultant. He essentially fixed GPS and got it working for the world, thanks to his understanding of the Sagnac effect and you can look at. You can look at the documentation yourself. One of the best exposés of it is probably Paul Marmay's GPS and the constant velocity of light. I think he puts it pretty well. He explicitly describes the c plus or minus v relationship that's there. What I mean by that is that the speed of light gets faster or slower depending on its inertial frame. And to simplify that, let's just say you're driving down the road and you shoot a light. Let's just pretend that light is traveling, which is a way oversimplification and a kind of a nonsensical way to look at it. But just for the sake of this thought experiment, you're driving down the road, you shoot a light out the front of your window. Well, common sense would tell you the speed of that light is going to be the speed of my car plus the speed of that light. But what they have to say is that the speed of your car is irrelevant and it's always going to be the exact same speed coming out of the front of your car. Now, with GPS, they actually rely on that traveling light, quote unquote, to determine the distances between the different GPS crafts and to try to figure out locations. And it turns out that as a GPS receiver is moving away from another GPS craft, and that other GPS craft sends the signal, sends essentially electromagnetic wave signal to the other GPS craft, which still applies. The whole C thing still applies to it. It's the same thing as the speed of light, according to all their math, and just according to what Maxwell figured out in 1865. All of that relies on, in order to determine precise locations, they take into account the motion of the receiver craft. So if the receiver craft is moving away, that speed of moving away has to be accounted for in the GPS range measurement. And so that alone is really, to those of us that are willing to entertain the thought, that alone should debunk relativity. But, Wang's in a lot of ways, Wang ended up in the same fight we're in, maybe a little bit less directly, because he was bucking the system. So in any case, moving on. The Elias effect and the anisotropy of space. So I'm going to talk about, we talked a lot about interferometry. Now I'm going to bring this to the pendulum, because in my estimation, it's the same. If it's not the same effect, they're tied in together, and they are perhaps just different manifestations or different aspects of the same thing that are causing these phenomena. But let's just get into it. So in 1954, there was a solar eclipse that happened, and Nobel laureate Maurice Elias had a pendulum going. And during that solar eclipse, pendulum going, what I mean by that is swinging and precessing. And during that solar eclipse, the pendulum started going crazy, had anomalous behavior. And he observed it again in 1956, and then again in 1959. The effect is still known today as the Elias effect. And so he wrote a book in 1997 called L'Anistropie de Space. That's the French name, the necessary revision of certain postulates of contemporary theories. And I like this bit here. He says, this book is dedicated to all those who do not consider today's well-established truths to be intangible and who do not have blind faith in their durability. And so this is the eclipse of 1959. Here is the total of the totality of the eclipse, and here is his anomaly. Here is him talking about how these anomalies are totally inexplicable within the context of the current theory. Now, this looks and reads a little bit odd because it's translated by an AI, which is unfortunate, because I would have loved to have had a better translation of this book. But if you can't, this book is very difficult to find, especially English translations. Apparently they do exist. I found out that after I had been looking for them for a while. Someone contacted me and said, hey, I have a copy of this book. So now that's exciting to me, but I've only found it for like over $100 available. It's a lot like Escape from Einstein by Ron Hatch, where it's just like you can only find it in really rare random spots for super expensive prices. And then if you go to Maurice Elias's Wikipedia page, this is a little off topic, but if you go to Maurice Elias's Wikipedia page and scroll down to all his books, he was mostly known for being an economist, but he did a lot of work with physics, and he was, like, there's a reason it's called the Elias effect. And you can't discredit a guy that took years of meticulous measurements with a pendulum just because he was a economist by trade primarily. Like, that's not how that works. We all know that. Um, but on his Wikipedia page, they have all his books listed. It's like a ton of books. The dude wrote a lot. And this book was written in 1997. All his books are there in order, but right where this book would be, it's just not there. They just don't talk about it on Wikipedia. It has been removed from history. So here's another one, 1955. So this would have been the second time he observed it. And here we go, standard days, which, what do you know? Doesn't this look like a daily periodicity? Huh. Does the Earth spin faster and slower throughout the day? And then during the eclipse, it just spins at a totally different speed? Huh. But so that's the Elias effect and has a pretty massive implication on gravity theories and the motion of the Earth, the rotation of the Earth. But on top of that, another thing Maurice Elias discovered was that the precession rate of the pendulum is relative to the sidereal motion of the sun and moon, which by that, what he means is their annual sky movements. So where they are in the sky is what's going to translate to the precession of the pendulum. And he says here, that's completely inexplicable within the framework of currently accepted theories. And then we have here a quote from the book. It is therefore appropriate to consider that the current laws of gravitation are in no way perfectly verified, definitive, and immutable laws on which one bases the assertion that my experimental results are contrary to all the experience acquired in the field of astronomy. These laws, like all experimental laws, are only verified with a certain approximation. And one thing I didn't include in here that's just kind of noteworthy is in this exact same book, Maurice Elias also goes pretty in depth into Dayton Miller's work from the 1920s that I mentioned earlier, the guy that measured the periodicity with his interferometer. And Maurice Elias did his own analysis of those measurements and corroborated Miller, agreed with Miller's findings. So he was operating as I'm not the only person operating within this framework that these things are connected with each other. Maurice Elias thought so as well, the guy that did the pendulum readings or took the pendulum readings. And so if you're wondering how this would work, just if you need a visualization, this is kind of how that would work. So you have your sun moving through here, and it's doing this on its analemma and going up. It's actually getting higher and lower and going back and forth throughout the year. And as it's going in this circle here, and the moon would be doing the same, similar, you kind of induct ether inwards. So let's say this is a racetrack of ether. This is getting inducted inwards and causing a spiral. And my estimation is that's why we have hurricanes that spiral this way and do this in the north, and cyclones that spiral this way and do this in the south. And it could very well be also why we observe pendulum precession to roughly fit sort of a similar geometry, right? Now, just if you get into the details on that, people will try to tell you that pendulums perfectly match Earth rotation, and we calculate Earth rotation using a pendulum. Always challenge them for their exact sources on that, and and really look, because it's not as straightforward as they'll pretend it is. And if they get you with one where it actually matched, they got lucky. Because they even have, if you go and look at documentation just for like a museum pendulum, they have electromagnetic systems in place to keep the pendulums in expected precession values. Because they don't want to have someone come into the museum someday and just suddenly find out, like, oh, what do you know? The Earth's not moving. That's crazy. No, they have a thing in place to keep it doing exactly what they want. And it's kind of crazy to think that they wouldn't have to have something like that, even if it did match a perfect Earth precession, Earth rotation precession, which, we won't go too deep into that at the moment, but even if it did that, humidity, wear and tear, like it's it's crazy to think that they wouldn't have to do something like that no matter what. But it's just my point is that this is not substantiated in the way that they'll try and gaslight you into thinking that it is substantiated. And but now the Elias effect, the periodicity, that has been corroborated. And here is a Harvard lab, Saxel and Mildred Allen, and in 1970, they published this, and here is them measuring the Elias effect. So during a solar eclipse, pendulum precession anomalies. So here's a standard day, that old daily periodicity, the Earth getting faster and slower, they would say, spinning faster and slower. But yet here is the Elias effect. You know, these are not the same. And they say here, so there's a relative increase of about 2.7 times 10 to the negative 4 were recorded, and that would require an increase in our tension of 1.2 kilograms. This is 5% of the total weight of the pendulum bob, and is far greater than the classical theories of gravitation can explain. Results of this magnitude have been consistently observed in Harvard over a period of 17 years. Our results are about 10 to the fifth times as great. So that was them in the Harvard lab. Here is Romania. This is just another corroboration, confirm once again the existence of the Elias effect. And then here's one where there are papers you can find where they found no evidence of the Elias effect. Well, this was the first one I grabbed when I went looking for, papers that were showing it to be disproven. And what do you know? It has a feedback amplifier that keeps continuous oscillation of the pendulum at 1 degrees amplitude. Okay. And then it also has an electromagnetic brake, which keeps the elliptic trajectory in acceptable values. Well, what's the Elias effect? Isn't it when the elliptic trajectory goes out of acceptable values? Huh. Okay. Well, let's see. Maybe they explain it. Well, no. Here's their conclusion: maximum deflection of the precession of the Foucault pendulum found in these measurements is very far from those obtained by Maurice Elias. But guess what? They never mentioned yet again for the rest of the whole paper: the electromagnetic brake. So the paper's essentially meaningless to me. Here's another paper. This is the cause of the Elias effect solved. And this is from Denmark. In this paper, they didn't do any experimentation, but what they did do is try to come up with a crazy new explanation for the Elias effect. And, it reminds me a little bit of relativity with this, because it's kind of the opposite with relativity, where with relativity, they're working on a bunch of alternative theories of relativity because they know it's utter nonsense. And at the same time, they're screaming at us about how relativity's been proven in every way possible. So it's like, why are you working on modified Newtonian dynamics then? Why are you, on the one hand, it's utter nonsense, and on the other hand, you're over here yelling at us for not believing it. Well, it's kind of the same thing with this, right? On the one hand, you're going to tell us the Elias effect is fake, it's unsubstantiated, Maurice Elias was a crackpot or whatever. And then on the other hand, you're going to be publishing all these papers about anisotropic dark flow acceleration. And there's another paper where there's actually, I wish I had that paper offhand. I can't recall where it is off the top of my head, but there's another paper where they try to explain the Elias effect. It's hilarious because first half of the paper, they're talking about how it has to be wrong, how the Elias effect has to be fake. And then the second half of the paper, they offer an explanation just in case you happen to measure it and it's real. So anyways, now moving on. It seems like, why are flat earthers so obsessed with relativity? Why are they so obsessed with ether wind? Why are they so obsessed with a pendulum? Why do they have to get so esoteric? Why do they have to get so out there in the weeds? Well, it's because, frankly, we're going up against a full lifetime of indoctrination, first of all, right? You went through a full education system, 18 years. We went through it too. We went through the same education system, and uh, we were taught the same things as you. We learned the same things about the solar system in elementary school that you did. The thing that we've come to find is that when you start digging into all these things, there's a lot to unwind. So we've basically got to dig up all of physics for the last 200 years or whatever. And we've got this just messy confluence of things that all are intertwined with each other. And what do you know? So we've got the curved Earth. We've got the ground beneath our feet moving. We've got 10 to the negative torr in contention with the Atmos. And all of these things are are utterly debunked by the ether wind, and they have to have gravity in order to have all these things make any sense. What do you know? The ether wind has been substantiated numerous times. Gravity has never been substantiated, not in the way in which they invoke it. Is there a downward bias on the earth? Do things fall? Yes. But their invocation of gravitation is uh, not substantiated, not on the quantum level, and obviously not on the large scale level, because we're not going out there and confirming any of these. I didn't get into Kepler's third law, but there's a really simple equation that they used to derive our entire solar system. It's all based on scaling mathematics that they can call dynamics because they threw a mass into their into that equation, but that mass cancels itself out proportionally with the way that they scaled Kepler's third law. So when you start thinking about Jupiter and Saturn and the massive they tell you it's an order of magnitude larger than Mars or something, and that like everything, there's these different orders of magnitude between all the quote unquote planets, and then one of them is made up of like an icy gaseous internals, and you have another one that's like rocky internals or whatever. Those are not based on anything other than Kepler's third law. So the reason they say that has to have a icy, Jupiter's moons are icy and gaseous or whatever, and that they have all these different chemical makeups. The reason they say all those things is based on the masses that they have to assume based on Kepler's third law. So that's how they quote unquote measured those things. It's not, obviously there's things in the sky, but what they tell us, what they assert to us about those things are what have not been substantiated. So moving on, let's now talk about the quote unquote curvature of the Earth. So in 2018, there was a laser test done by FE Core in Hungary and the Netherlands. And here's just some photos showing their setup. And so this is the measurement procedure. Here was the receptor of the laser beam. That was the target essentially. And so we're going to talk first about measurement 1, and then we'll jump to the last measurement 7. So this was measurement 1, and they went across Lake Balaton here. And they talk about geoid undulation. They took all this stuff into account. Geoid undulation is the term used to describe the distance of the geoid above or below the mathematical reference ellipsoids, the WGS 84. And in this particular location where they took this test right here, the geoid undulation was at the same level in both positions. So that's not what that didn't affect their measurement. And just to show you right here, they were 4.92 feet above the lake surface, and they were able to see the beam and record it 12 kilometers or 7.46 miles at 5.25 feet above the water level. And that should have been, according to Globe Math, under 15 feet of curvature. And then here's a picture of the laser beam from the side. They just to show, they were able to just visually kind of check and spot check and say, oh yeah, it looks horizontal. And then here's measurement 7. You have target 4 position. So this one was 9.58 feet above the lake surface was where they emitted from. And then it was seen on the opposite side, 25 miles away, 4.92 feet above the lake surface. And that should have been 297 feet under or hidden behind, quote unquote, curvature of the Earth. But they didn't. So I've actually listened to a couple of contentions on this. The best contention I've heard is that the laser somehow skipped across the water and perfectly hit the receptor. At first, some people will try to tell you the laser scattered. It hit the water and then scattered out. So they actually only received a small portion of the beam at the receptor, but they actually had full laser strength at the receptor. So it's not a scattering that's happening. Hopefully you don't buy into the skipping across the water thing, because that's never been substantiated. But yeah, so that's what happened there. And so here's their conclusion. All large bodies of water should follow the geopotential surface. We proved that these lakes are non-uniform with the WGS 84 model. So water should be curving in line with what's expected from WGS 84. And the model's incorrect. And really what they showed there was that it's pretty dang flat. But you ask me, don't we see boats go over the horizon? Like, I'm pretty sure I've seen that before. I know some people that told me they've seen that before. So, I'm not gonna call those people liars. They would have no reason to lie to me about that. And I've definitely seen the sun set at night, right? Like, so where does the sun go at night? How don't boats go over the horizon? Like, those are fair questions if you're asking them in good faith. So let's get into that. Um, and it's actually, in my opinion, not so complicated. But some people, I don't know. It's just let's get into it. So we don't actually see infinitely in all directions. We don't see perfectly 3D. Uh, we see from a single point. You see out your eyes, right? You see from inside. You have your head looking out your eyes, and your eyes are two lenses, and your pupils are like two little inlets where you have your aperture, and you see out from that point. And the way that works, we have a resolution limit because you can't see forever. So we perceive from a single point in 3D space. And then as you go outwards, angular resolution imposes a nonlinear drop off in our ability to resolve items as they move away from us. And your ability to ascertain objects dissipates or disappears into an unresolvable angle in a nonlinear fashion. And I'm just going to jump ahead really quick here to this to kind of try and explain this a little better. So you see this guy looking out here. Well, as your range of vision goes outwards, what happens? Well, here we have a small circle, right? So you don't have that many objects in your field of view. You don't have that much area in your field of view right here. So things are going to be big and right in your face, right? And then as something is further and further away from you, that happens in all these directions in your full field of view. So let's take periphery out of it. You can take these little chunks out. You can take your periphery out. So you've just got this little area right here, right? Well, as you go out, what happens? This expands. And as this expands, you now have less room on your canvas or your computer monitor or whatever to resolve things. So one analogy I've used in the past is you can think of it like a computer monitor. And let's say you have a window open, you have Microsoft Word open, or let's say Open Office. Let's say you have Open Office open, and then you want to open up Firefox as well. Well, now you're going to move Open Office over to the other half of the screen, and now you've got Firefox here, Open Office here, and then you're going to open up, say, Discord. And now you're going to move those down. You got Discord here, and then you're going to open another application, another application, another application. And next thing you know, you're moving all these. You're trying to keep everything on the screen. Well, you're going to get, as you keep shrinking these windows down more and more and more to get more things on your screen, eventually you're going to hit the point where you're down to your last pixel. Everything's one pixel on the screen. So when you get smaller than one pixel, when you're way out here and you've got a giant mountain right here and you've got a person right here, they're just going to both look like less than a pixel because there's too much for you to resolve. Your monitor can't get bigger. Your eyes, your vision of the amount of light you can take in can't increase. So that's hopefully that's a clear explanation of that. But just to go in a little more detail here, we learned about it in sixth grade. It's just the idea of perspective, and it's that these train tracks don't actually converge, right? We know that. It looks like they do. That's an optical effect. That's a result of what I keep saying about how we perceive from a single point in 3D space. Now, if you could be all knowing and all seeing and go hover above the entire world and somehow just like conceptualize all of 3D space in your head, then these are going to look parallel. And you're actually going to see in quote unquote Euclidean space, right? You're going to see in Euclidean geometry. But that's obviously not how we see because we see out of a single point. And that's not how any optics work. Cameras, telescopes, all of them come out from, one or two lenses. And they all have the same issue. Now, if you have different aperture rates, different focal lengths and stuff like that, you'll get variations of this, but you're always going to have the effect. And so here's a paper, Hyperbolic Geometry in Binocular Visual Space. In this paper, we are going to explore hyperbolic geometry and hyperbolic models of binocular visual space. In hyperbolic geometry, all the axioms of Euclidean geometry hold except the parallel postulate. And that's a pretty massive postulate because when lines aren't parallel and things are converging, that's going to change the geometry of everything that you see pretty drastically. And then they do indeed show that binocular visual space may be best explained by a hyperbolic model. Here's kind of showing what this would look like. This would be, I guess, kind of near midfield. But you see how you get the curve, right? And this is how we see our brain kind of processes it, so we don't perceive curves everywhere that we look. It doesn't, it doesn't stand out and distract us or anything like that. But this is just plain and simple how we see. And this is why when you go to take a photo of somebody, you wouldn't get right up in their face with a wide angle lens, even though you'd have the same field of view. If you're going to take a portrait of someone and you want them to look nice, you would stand further away and you would use like a 55 millimeter lens, because they're going to appear a bit more squared. They're not going to have this curve that you see here. Now that curve relationship is not, it's actually pretty complicated, because, well, so this we kind of already talked about. This is the idea that, these are actually parallel lines, but to us they look like they converge. But so here's kind of showing. So you've got this curve inwards at the outer, or at the closer edges, right? And as you go further out, see how it's curving outwards. So this is them actually mapping how the curved visual space works. And they say, without any more calculation, the raw data thus reveal the optical space is elliptic, positively curved in the near zone, but hyperbolic, negatively curved in the far zone. Uh, and it, so I guess I took out the actual showing them doing the experiment, but essentially they just had people stand far away from a pointer device, and then they had them try to visually perceive where the pointer device should be pointed. And they also did some analysis of the famous alley experiments. And the famous alley experiments also demonstrated via people standing in an alley and looking down the alley through, I believe it's a line of torches, and they had to try and line the torches up parallel to each other from the distance. And that experiment also showed we obviously don't see in Euclidean. Like I said, man, we learned this in sixth grade. And I know, like, when you start getting into the details of it, it gets a bit complicated, but just intuitively, we should all know, right? Things converge in the distance. You take those train tracks, you flip them on their side, you got your horizon, you've got your sky, you've got your ground. There's your horizon converging in the distance. And then here they say, we shall now perform one step further, or one further step of data processing that is of a more complicated nature. Given the intrinsic curvature as a function of distance, we proceed to construct a surface that can be depicted and has the same intrinsic curvature as the horizontal plane at eye height. So they're going to calculate curvature using optics. So that covers kind of the physical, specifically the physical curvature, which is technically geophysics. But now we'll get into some more geophysics outside of curvature. So this is globular plate tectonics, another thing we learned about in sixth grade that we were indoctrinated with. And this is how, now, maybe there's something to this. I'm not totally, I'm not, I certainly wouldn't make an assertion about this, because I've never been down there and, actually felt a tectonic plate. Now, is it a model that could have some value? Sure. But in any case, this is what they invoke. This is built into all of their assertions, their magnetogeology, their geology, uh, their geodynamo, all of those things. These things are all build upon each other. They all kind of borrow and lend from to and from each other. And this plate tectonics thing, you have to think about this on a rotating globe. If these things are sliding around and our Earth is rotating and we have a semi-liquid interior, what should a maximum momentum, minimum energy state look like? Because that's what a rotating sphere should do. It should find its maximum momentum, minimum energy state. And really, what should happen is that the greatest masses, the continents, should actually drift outward to align the equator. Not, it shouldn't really do what they say Pangea did. So getting into Pangea, this is what they say, right? This is built into all their assumptions. They have their model with Pangea, magnetic striping on the ocean floor, sedimentary rocks, and carbon dating, and all these things all come together to paint their picture of their Earth. But the thing about Pangea is, you go back to what I was saying about the maximum momentum, minimum energy state. Like, you have all the land masses on one side. That's going to cause like an insane instability, especially when you pair that with a semi-liquid interior, and you're not going to have uniform rotation. And that's, like I said, this is foundational to all their geophysical assertions. So, could the continents potentially have drifted apart or been drifted apart or something? Sure, but in the context of them asserting their time, the amount of time that they have asserted, and a rotating sphere, or spheroid, it's not very coherent. And so with magnetogeology, they rely on what's called, I mentioned, the magnetic striping across the ocean floor. And these are just unsubstantiated assertions. Essentially, as magma is coming out from points in the ocean floor, they look at the rock formations adjacent to that, and as they move outwards from there, going out through the adjacent rock along the ocean floor, they see stripes. And so they have concluded, based on nothing that they can possibly substantiate, that that's due to pole reversals of the magnetic field. So as the North Pole and South Pole flip every 750,000 years or so, according to their model, the magnetic striping then shifts as well. It's basically the way that the magma cools, according to them, looks different depending on which side of the Earth the magnetic fields are on. But those pole reversals don't match geodynamo predictions, and the geodynamo itself is built on ad hoc assumptions, offers no predictive value about what the magnetic field's going to do. But my main point here is just to show that all these things just kind of complicate each other and make the whole thing kind of a noodly mess. The geodynamo model itself is crazy. This is how they explain the spheroidal Earth's, or the globular Earth's, convection or magnetic field. Because we all know Earth has a magnetic field. Now, they'll tell you it has two poles, a North Pole and a South Pole, and your compass is going to point to the North Pole. But it's kind of weird because when you go south, your compass doesn't point to the South Pole, never does. And then what it actually seems to be is that your compass actually aligns itself orthogonal to the electrical current of the Earth, going in its vector, in its essentially, what would it be, west to east vector? It's
East to west,
uh,
downward vector.
yeah, thank you. So yeah, downward as well. So in any case, that's what they invoke to. So in order to explain the magnetic field, they have a crazy model. It's called the geodynamo model. Basically, they have their solid, hard iron core in the center of the Earth, and then around that, there's these whirlpools that turn of molten magma. And as those whirlpools are turning, it's generating static electricity and it's generating static currents, and that's causing a magnetic field to emerge from those points, uh, thanks to those convection currents. Well, interestingly, those convection currents. So, in order to explain why those convection currents turn, they say it's because of the Earth turning. They say it's Coriolis. That's why the convection currents turn. But then why is this is the rotational axis of the Earth? And in their geodynamo model, this is the axis of the magnetic field. So the convection currents, though spinning due to the Earth spinning, don't spin in line with it. They have their own rotational axis. Because why not? And so this was something I just wanted to get into. I won't go too into detail on this, but they will try to invoke PNS wave shadow zones as proof of the globe. Now, if you can look here, I think it's kind of intuitive that the S wave shadow zones are just, that works on a flat Earth. That's just moving outward from the epicenter. And then with the P waves, they try to invoke this model. They will try to claim that this has been substantiated numerous times, blah 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 blah. And they've got this, essentially similar to the S wave zone, but then they've got this thing where they say it propagates through the core of the Earth. But then you have these shadow zones. So this would be like, they would say on one side of the Earth, this would be the other side of the Earth, and they say that this is proof of a globe. But I don't know about you. When I look at this doesn't seem very. This doesn't make me feel like they've got a very good handle on things, especially when you know about how all these things are just kind of piled on top of each other, anyways. And so, and of course, they're going to tell you it's proven. It's proven. It's, we've got the math, this and that, blah, blah, blah. And they know when they do that, that this stuff is buried in crazy named papers. It's buried in, in admittedly very complicated math. That's by design, right? They don't want you to go, they don't want us to be, like, why wouldn't they want to share this information with us? It's like with all these things, right? Like, why is it all gate kept? It's kind of odd. But in any case, move on here. So I'm just going to read this quote from Sir Karl Popper. When you see these these epicenter or these waves crisscrossing each other like this, and you see just this crazy confluence of a theory all coming together that you can't falsify, because as the thing gets more and more convoluted, they just keep layering on top of it. So I thought this was just like a really good quote. It says, "Insofar as scientific measurement or scientific statement speaks about reality, it must be falsifiable. And insofar as it is not falsifiable, it does not speak about reality. Because how are you gonna prove something if you can't attempt to falsify it?" And so now I'm just going to talk real quick about just a few other theories about how earthquakes work, and how, just kind of illustrating, hopefully, that it's not so simple. And they assert like they know, but they're so much more complicated than they realize. And this says the position of the moon in its orbit is primarily related to the seismicity of the American continent, which released more than 82% of the global earthquake energy of a magnitude of more than 8.4 during the northern lunar declination. So the moon is affecting earthquakes. And actually, if you look into this, it affects particularly the very heavy earthquakes, right? The high Richter scale earthquakes, high magnitude. They are highly correlated with the moon. And then also, here's another paper saying that space weather and earthquakes possible triggering of seismic activity by strong solar flares. We can suppose that the earthquake triggering due to impact of strong solar flares is possible. It's not clear today. New fundamental knowledge is needed on the mechanisms of interaction of the electromagnetic field with rocks, as well as on the influence of electric/electromagnetic fields in combination with natural geophysical fields on deformation processes in the fault with specific parameters, electrical conductivity, orientation, and maturity for earthquake occurrence. And so this is now how they compute their globe, right? Using seismology. They were saying that they have this, they have proof of this, they have proof of the readings, seismometer readings of these vents, propagating out exactly in line with, uh, with their expectations. But unfortunately, I don't have the sources up for that. But I was able to find 4 sources of where it didn't line up at all. And actually, in all 4 of those sources, they were massive earthquakes, and the seismometers across the world were picking up the readings of the earthquake before the seismometers right next to the epicenter. And it was totally like, that's not in their predictions. And that's the way these things go, right? They're not going to tell you about when it's not in their predictions. They want to tell you about when they got it right, just like the pendulum, right? Oh, we did it. It matched the globe precession. Okay, what about like the 100 times that you didn't get it right? What about the fact that the museums have to put an electromagnet, have to put a mechanism in there to make it precess at the rate that they want it to? Well, here we've got this, right? So uh, this is called, and it's like, I'm never surprised when the papers that actually explain the most and give you the most truth have the most convoluted names. 2D, 3D, multiplied, transmitted, converted, and reflected arrivals in complex layered media with the modified shortest path method. That's what this paper's called. And what they're talking about by 2D, 3D is flat Earth versus globe Earth. And in case you don't trust me on that, here we got the code of the multi-stage FMM is Cartesian coordinates for 2D models and spherical coordinates for 3D models. But they get the same solution accuracy under less CPU time with an order, but the computations are faster when they use the 2D model. And more importantly, I think that what this paper reveals is that in their 3D model, they use what's called a multi-stage scheme. And that treats each layer of the wave front, meaning like the seismological wave of the S wave, enters an independent computational domain, and one obtains a transmitted and or converted branch of later arrivals by reinitializing it in the adjacent layer, and a reflected and or converted branch of later arrivals by reinitializing it in the incident layer. So as it's moving through these different layers of the earth, right, of the core and the outer core and the things that they say cause the shadow zones, as it's moving through those things, they're not even doing it in a uniform computational way. Every single layer that it goes through, they reinitialize the whole thing. They can redo their math from the ground up in each layer, and they have no problem with doing that. So you get to a point where, at what point, when all the layers are being hypothesized in the first place, and you're reinitializing your math through in each of these layers, you are making a statement about nothing because you've never substantiated what you're using to prove your theory, right? It's more begging the question. And what do you know? They do it for computational. This paper is about computational efficiency, and that's just showing this is all being computed. They're using computers to do this. They're not. This is not some simple equation where it's like, oh, look, dumb flurf, seismology only works on the globe. No, 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 buddy. You're using a super. You're using a supercomputer. Cool. And one thing I said during the debate that this is all kind of from is that uh, if you give me a neural network, a supercomputer, enough computational power, I'll give you a seismological model of anything. You want a donut Earth? Sure. You want an ice cream cone Earth? Sure. I can compute it with enough power, but what does that tell me about reality? It's just like the Laser Interferometer Gravitational Observatory, aka LIGO. They do this to a whole nother level. They have a whole convolutional neural network that they use that everything gets filtered through. And this is just what all of modern physics has become these days. But in any case, moving on. Uh, One thing I just recently learned within the last couple months here was about Newton's shell theorem. And this is the idea that where we have the Earth's dense iron core, that point where, okay, so remember how I kept talking earlier about how everything is ad hoc and they have all these confluence of things that sometimes agree with each other and most of the time don't. And they just keep wrapping it all up and, adapting their theory ad hoc, another explanation, another explanation. Well, they have to have an iron core in the center of the Earth because if they don't have the densest part of the Earth, the dense iron core right in the center, then they can't have us all being pulled uniformly downwards on a globe. We would all be, if the greatest gravitation or the densest point of the Earth was at the surface, then it would be, wherever you had mountains, wherever you had more like a lump or, the geoid would be throwing gravity off everywhere. And according to Newton's shell theorem, it's actually the surface of the sphere that should develop the greatest gravitational potential. And in the center, where they have the most dense, where they invoke point specific gravity, at that exact point is where it's supposed to be zero gravity. Okay. So this is easy to explain. The gravity downward motion is easy to explain with a uniform downward bias. And that would align with the downward electrical current that we measure that comes from the atmos. It's objectively measured. And this is also why the voltage gradient lines across the Earth are parallel to each other and they're perpendicular to the ground. And they're not oriented as concentric spheres. And if they were, they wouldn't be. It wouldn't go up at 100 volts per meter. It'd be way off from that. It would actually have a relationship that would scale in relation to the size of the sphere growing. Because as the size of the sphere grows, the potential changes. And if you think about it, with concentric spheres, it's like you think about the Russian dolls, and each Russian doll outside of the other one is bigger, right? And so you'd have more area to what's the word I want? You'd have more area to cover essentially, and so it doesn't work parallel and perpendicular, and yeah. So, anyways, moving on. That's pretty much everything. I'm gonna close here with I'm just gonna be honest, because I don't want to lie to anybody, and this is still my hangup. This is if anything was gonna pull me back to the globe, it'd be this. That's Apollo 17, and it's pretty. How you gonna argue with that? I am a little curious what happened to the camera guy because they panned up, so they must have left him on the moon. But I'm sure he's got a little station out there. But anyways, thanks everybody for listening, and yeah, that's my presentation from Saturday. And I
Yeah.
think
Bravo.
now, what's
Ton
that?
of inf-
Yeah. Bravo.
ton of information in there.
Yeah, yeah, it is a lot. Should I real quick? I can pass it over to you when I'm done. But real quick, I'll just touch on the neutrino thing. So now that's pretty much the end of my presentation there. Me and Alan are going to go through a few things now and just provide some clarity and context for a few things that got brought up during the debate. We did get a chance, thanks to Witsit for having us on Saturday to right after the debate to talk about it. But we're going to go into a little more detail now that we had a few days to kind of think about things, go through things. During the debate, I got gaslit into being told that cosmic rays had nothing to do with neutrinos, and that like the fact that I would invoke cosmic rays as a response to neutrinos was like proof that I didn't know what I was talking about or something. But like I'm not going to go into real big detail on this because the fact that I even got kind of baited into talking about that was a waste of time probably. But these were all papers I had before. Like you can look at the date added. I've done research on this in the past. These were the ones I added today just because they had like what do you know like cosmic rays reviews are astrobiologists. So let's open this one up. This one talk about neutrinos. No. All right. So in any case, neutrinos and cosmic rays. Neutrinos from cosmic ray interactions with the sun. This is quite specifically what we talked about during the debate and that they tried to tell me didn't exist. So just in case anyone's not real sure about that, here's some papers about it. And just kind of explain like how that actually works, what that discussion was. Essentially, they tried to invoke the fact that there are neutrino receptors that exist on the Earth that they can point at the sun, quote unquote, through the Earth and measure the reception of neutrinos from that point. But I asked when he brought that up, I said, "Oh, that's interesting. How do you know that they're coming from the sun?" Because my understanding is that cosmic rays come from every possible source in the sky in every possible direction, to the point that they even have random number generation. They have concepts of random number generation built purely around observations of neutrino or of cosmic rays. Um, but so what they tried to then tell me was, oh, the neutrino is different. Well, the neutrino cosmic rays can be literally anything. Like you go look it up. It's actually really, really fascinating the more you start looking into it, because literally they say these things, cosmic rays, they can come from any direction, anywhere in the sky, anywhere in space, the sun, wherever. And they can be basically anything. Like it can be neutrons, it can be protons, it can be basically anything. But the neutrino is a relative phenomena to, like, you don't have neutrinos without cosmic rays. That's where the input is, right? That for the phenomena of neutrinos. So in any case, just want to clarify that. I think that was pretty much everything that I wanted to clarify on. Yeah. You want to go ahead and take over, Alan?
Yeah, so somebody emailed me with some questions about the oscillation rate and like what it means for the clock to be retarding proportional to its velocity. So I kind of wanted to go and give a visual detail on that because it is a significant detail to the argument, but it's like getting a good concept, a good visual understanding of what it even entails will really help. Explain the words that are being said, right? Because you can explain it, but it's like if you don't really see it, like you don't, very difficult to make sense of what's going on. So I got screen share here. That'll probably help. That should be, you guys see that?
Yep.
All right, cool. So this is the old atomic clock. So you can kind of imagine one of these being set on a craft, whatever, and then all the magic happens in this chamber here. So we have a diagram of the chamber. I want to switch over to a paint program so we can kind of edit the path of a cesium atom. So before we get into that, though, the way that they talk about how the atomic clock functions, they use their atomic model, and it works off of manipulating the valence electron. So if you go to the atomic model, there's cesium atom, and then at the top here, the valence electrons that are available per atom or whatever are here. So this is they've chosen cesium so they can get this one free electron or whatever, so they can edit that. That's how they talk about it. That's how they explain it. So I think it'll be much easier to just look at it as a wave and it's just oscillations. So when we get into that, I'm going to bring that up now, and we'll talk about the whole process of how they synchronize one of these clocks. So before we get into Einstein synchronization and how GPS keeps time, we'll get into just how a singular clock would function, like how, like, from turning it on to getting it synced up, right? Like what happens in this chamber, right? This mysterious chamber. So in here we have the cesium oven, right? So they just have a little vial of cesium, and this chamber's vacuum sealed, right? So once the vacuum seal breaks, the little cesium vial breaks and they heat it up, and then it emits vapor from it, right? And they have like this this exit here to get out here is collimated, so it gets focused into a fine point. We have cesium vapor leaving the cesium oven that's excited. It hits, there's magnetic fields here, right? So anything that is oscillating too fast, like if it's vibrating too fast, it gets bounced out. If it's vibrating at just right, then it goes through the magnetic field. Once it goes through the magnetic field, it enters the, what is this called? The radio frequency chamber or something like that. Anyway, it'll be in this radio chamber here, chilling, building up, bouncing out, and it oscillates at a specific rate. So when it gets excited and comes out of this oven, you can think of it like it's vibrating, right? So it's vibrating at 9,192,000,000 times a second. So anything that's vibrating faster than that or slower than that gets deflected out. Anything that's at that proper rate gets to go through the field. Then once it's through the field, it enters this radio cavity here. Now what they do here is they send, let me change the color here. They send radio signals out. Oops, didn't change the color at all. Blue. There we go. All right, so they'll send radio signals in here and they will mix with the excited cesium, right? So when the oscillation rates of the microwaves that they're sending in match the oscillation rate of the cesium of 9,192,000,000, they'll be, you know, in phase or whatever, right? So when that happens, when this builds up, they leave the chamber. I don't have a combination one here. Let's just make it green. So when the cesium vapor oscillation rate and the microwave oscillation rate matches, it gets ejected from the radio chamber. So this magnetic field, so anything that's vibrating faster than 9,192,000,000 oscillations a second or slower gets deflected out, and then the proper rate hits the ionizer, right? So that vapor and the electromagnetic wave gets ionized, and that ionization gets they send that to a, basically they call it an electron multiplier. It's basically like an oscilloscope. So what's going on in here is this is converting the ionization into an electric signal, and it's bouncing it around so that it could get like a reading on the signal. It's like amplifying it, right? So when they get that signal, it's going to read out that there's an oscillation rate that they've converted into an electric signal that oscillates at 9,192,000,000 vibrations per second. And that's how they keep time. That's how they lock in. That's how they break a second into 9,192,000,000 of a second, essentially, right? So once they have this rate locked in or registered, they lock it in. So this will start putting in, the same output as the vapor, so that it matches up. And so now that they've got this like locked in, right? So imagine this is just stationary, right? So we're all locked in. We got our oscillation rate. Now we get into what happens when it's moving, right? So imagine this in a craft. Now it's doing its thing. It's, if it's on a globe, it's falling around the globe. If it's on a flat earth, it's going around like this, right? Either way, it's also another effect is happening, right? This oscillation rate that's supposed to be the same once it's all locked in and according to relativity theory, right? There should be no additional retardation given like velocity or anything like that, right? Well, what actually happens is, for how fast the craft that's carrying this clock is moving, the oscillation rate drops proportionally. So if the end result of this radio cavity chamber and magnetic field and all this and ionization is to produce something that's oscillating at 9,192,000,000 vibrations a second, right? But then for some reason, like let's say this craft is traveling at 10,000 miles an hour. Well, now it's only oscillating at 9,182,000 times a second, right? So they have to input additional energy in here to compensate for that, to keep it in sync. Now, relativity theory says that shouldn't have to happen, right? There should be no retardation proportional to the velocity of the craft as it falls around the Earth or as it's moving around the Earth, right? So they specifically define the orbit of a satellite as a local inertial frame in free fall. So once this clock is synchronized, if the one-way and two-way speed of light, if c equals c, right, regardless of the motion of the observer, and you're in an inertial frame, because keep in mind there is some motion here, but if you're in an inertial frame, right, especially a local inertial frame, your c is going to equal c. You're not going to be able to use the velocity of light to detect motion according to relativity theory. But what actually happens in reality is these clocks retard proportional to their velocity, and that needs correcting. So the idea, and they're keep in mind they're free falling around space, like in their model, right? How they would explain it to us. So there should be no reference for them to get a velocity, right? So earlier, Toby was talking about how your car needs to monitor how many times the wheel turns, right, to get a velocity to know how far it's gone, etc. Well, in the same respect, if this satellite's free falling around the Earth in an inertial frame, there should be absolutely no indication of how fast this thing's going, but you can actually deduce the speed of how fast it's going based off of the clock correction required to keep it at the oscillation rate required to maintain GPS time. So hopefully that makes a little more sense with the visuals and it being a wave, because the way that they try and talk about it through this model, and you got your electron that's just out there hanging out, and they're like, well, the we're just after this one electron. Like, nah, forget about all that. Just think about it in vibrations per second. That's all it is, essentially. So if there's any questions, comments, or concerns, feel free to chime in.
I just throw in that the relationship of that retardation is the same relationship of the, quote unquote speed of light that they have to account for with the inertial frames of the GPS crafts. It's the same effect. So as the clocks are moving east to west or west to east, they gain or lose time depending on their direction, just like the quote unquote speed of light and electromagnetic waves gain or lose time depending on their direction. And then just like the quote unquote speed of light that it gains or loses going east to west and west to east, it also does not gain or lose at all going north to south, directly straight north to south. That's speed of light, and that's the atomic clock, because essentially it's the same, very similar relationship, right? It's essentially the Sagnac effect. But yeah.
Yeah, 100%. And another thing to note, like not to make it too confusing to end off of that, but that north-south relationship, right? So this whole thing is based off of like the way that they'll try and explain it. Well, C is C, right? But the Earth is physically rotating, so therefore the distance is increased, right? So they're like rotated. But when you do north-south propagation, there's no variance, there's no displacement. That's not possible if the actual reason for the Sagnac correction is that the person is in a different physical location because the Earth is rotating. Irrespective of an east-west rotation, you're still going to have a variance on the north-south side of it. But
Yeah,
yeah,
and real quick, sorry, I accidentally left myself muted for my stream there. What I said was just that the atomic clock retardation is directly proportional to, it's the same thing as the quote unquote speed of light going west to east or east to west. It goes faster one way, slower the other, and the atomic clock retardation rate is the same thing. It's relative to its motion going east to west or west to east, and it gains or loses depending on one way or the other. But the speed of light does not go any faster or slower north to south or south to north. It's the same. And it's the same thing with the atomic clock retardation. It only gains or loses going west to east or east to west. But yeah, sorry for being redundant there, but I just want to make sure I got it into my stream.
You telling me, Alan, that microwaves or EMF of any kind is cooking faster the higher it goes? You telling me that they're making corrections for the rate at which a known stable
oh,
oscillation frequency is changing?
yeah, based on how fast it is, right? So they have like their equipotential gravitational, what was it, correction, right? For that retardation that they say is due to the gravitational potential of the old geoid, right? So they've already got that baseline covered, and then they're talking about now, or not talking about, but then yeah, what we're talking about is the additional velocity correction that is, that they have to account for.
You're telling me that they claim that it's because of the motion of, Earth and all that, but then it doesn't happen north to south? What?
Yeah,
So
I don't really understand it myself because
so
it's
one
just. Oh,
second.
go ahead.
So for signal propagation, like from something being sent from the satellite, there's no north-south variance, right? If the satellite is moving north-south, it still has to correct proportional for the retardation proportional to its velocity. When it's moving north-south, there's an additional component that's required to correct for it, and that's in Marmot's paper. I could pull that up real quick to explain that. So again, for signal propagation, there's no variance, right? Because it's just being sent like in quote unquote free space, right? But if you're actually moving in that direction, there will be a variance proportional to your velocity. But that additional correction that they would input for Earth rotation is a non-factor for signal propagation. Does that make sense now?
Oh man, so the Einsteinian gravity well of Earth is grabbing it when it moves north south and keeping it
No,
proportionally
only. Oh yeah,
attached to the surface
yeah.
of Earth.
Yeah, it's a gravitational anchor point or whatever. So yeah, let me bring
Just
up the
for the benefit of the viewers, I wanted to ask those questions
No, you're good.
because
Thank you.
like,
No, you're good. So, like the clarification again, right? Because Toby kind of misspoke a little bit. If the craft is moving north south, it still has to account for its velocity. If it sends a signal north south, there's no additional SAGNet correction that needs to be made for the signal. If the signal was sent east west, then there has to be a SAGNet correction. Now, what's really interesting about the SAGNet correction that they apply is that it's not a velocity correction. It's actually them rotating the coordinate system. They're inverting the time and distance axis on that. So it's not even this. It's not even a. It's not a contraction mechanism. It's not anything related to what would be a traditional velocity correction. It's or what you would say is due to a relativistic effect even. Right? Because that's not the same thing.
so they don't length contract or time dilate the signal to get a different velocity of 3 milliseconds or however far. They just rotate the reference frame. They say so hold on. When we send the signals from the GPS satellite, it's so energetic it causes the Earth to shift by a few nanometers. Rotating the reference frame.
They don't
That's
even
interesting way to look at it.
Yeah, they don't they if correct me if I'm wrong, Eric, but they don't even really give an explanation as to why they do that. It's just you just do it. Just in the correction manual or like, on the list of stuff you have to include.
But that's what it would be equivalent to, right? If you rotate the reference frame, what's the reference frame? Well, the Earth, right? I mean, like,
The
if we were
ECEF. So essentially they're compensating for the Earth not rotating.
I believe that, excuse me, the compensation is given in that interface specification that I sent you the link to about an hour ago.
All right, check it out here in a second. Let's see. Actually, it's actually lower. So yeah, when he's talking about the signal propagation and the corrections that they make for the atomic clock here, they're all like all these equations he goes over. They're all just different iterations of how you would account for the Sagnac effect. So when he references equation 13, go all the way back to 13. Yeah, it's literally just accounting for the Sagnac effect, the whole thing. So all the clock corrections for keeping the clock in the clock that's on the craft in sync. That's just a Sagnac correction.
Yep.
That's wild to me, bro. That they do the transform or the rotation of the reference frame though, because since they've already Einsteinian synced, right? They're not supposed to need to perform any other corrections, and so I guess they explain it that way because otherwise they'd have to admit that they're directly adjusting for the velocity.
Yeah,
because I mean that is what they're doing, but I mean it like they don't want to say that.
Yeah, that's 100% it. And your boy Daniel Garzi points that out in his paper here. We'll go over real quick. Sorry.
And real quick, while you're pulling that up, just we talk about this paper a lot, and people will Globers will say, "Well, he says this, this, and this in the first half of the paper." Like, the first half of the paper, Paul Marmé is trying to like offer an olive branch to relativists essentially, because he's trying to give his own brand new physical interpretation of how these things could, because he's recognizing the fact that these are classical effects, and then he's trying to give a relativistically themed explanation for these classical effects. And so even to me and Alan, when we read it, we're like, okay, this stuff's kind of nonsense. He's talking about like things physically getting smaller and shorter, like within, to explain relative simultaneity. But that's not the meat of the paper. The meat of the paper is the actual math showing the Sagnac corrections and showing the way range measurement works and the way that atomic clock decay works.
Yeah, going over why he even has to propose or affix to it anyway for the logical inconsistencies, right? Based off of the practical application of how they had to sync clocks, right? It directly refuted Einstein's synchronization. I was actually reading I'm not going to get into it. I'm going to read this out and then we should be good to go. So this is from Daniel Garzi, and he gives his take on a paper that was written by Wolf and Pettit, where they go to Colorado and they analyze the raw GPS data to see if C equals C or if there's some variance in it. So we'll just read it from the top here. One of the most familiar arguments for the validity of special relativity is that the global positioning system, navigation system, would not achieve a high accuracy without making special relativistic corrections. The principal correction cited is a first-order timing adjustment to compensate for the signal propagation time variations arising from the motions of satellites and the ground receivers on the local Earth-centered inertial frame, Earth-centered Earth fixed frame, due to the Sagnac effect. But the Sagnac effect is purely a classical first-order effect that has somehow been incorrectly reclassified in its application as a special relativistic effect. See Alan, Weiss, and Ashby. So this Ashby guy that I was talking about earlier, they did some experiments with Alan and Weiss where they, found that they had to make some quote unquote Sagnac corrections to keep C equaling C, right? So they have this guy Ashby going out 20 years after that, like, every couple of years, he's just like going on tour, basically telling everybody how Sagnac effect is proof of Earth rotation and all this stuff. But we're going to get into how that's not what's going on here, because they're actually applying a correction to the speed of light to make it appear as if that's what they're accounting for. And you wouldn't have to apply a first order velocity correction to the electromagnetic propagation if relativity theory were true. This is huge. This is like a huge slap in the face to relativity here. So first order timing corrections must be made for the accurate performance of the GPS system. Just the amount attributed to the velocity component of the satellite constellation along the line of sight in the ECEF frame. The fact that a first order timing correction is required at all is in direct conflict with special relativity. So now we're going to get into the two lads that went to analyze the data at Colorado. The Wolf and Pettit, 1997, tested the isotropy of the one-way speed of light by analyzing the GPS satellite network timing signal database, and they found no dependency on the source receiver motion, which they interpreted as evidence that the speed of light was isotropic. However, Wolf and Pettit noted that the dataset that they analyzed has been pre-processed and corrected for the Sagnac effect. In this case, a first-order change to the time of flight of radio signals between satellite and receiver, and justified in making this correction by claiming that the Sagnac effect was a relativistic effect that was a second order in C, and therefore that the correction had a negligible consequence on their analysis. But the correction that was made was of a first order velocity component in the line of sight between each satellite and the ground receiver in the ECEF frame. Thus, while the effect of the first order line of sight velocity component of the satellite is clearly evident that the raw timing signal data in the first order component had been removed from the dataset, Wolf and Pettit analyzed to show that C was isotropic. What do you know, boys?
It's like, I forgot that that's what they were doing, was like literally analyzing it to see if C was isotropic. Like, hey, we removed all the isotropy or all the anisotropy. Here's your data set to check for anisotropy.
All right, here's your data set to check for isotropy. And then they're like, oh my God, no way, we found it. And then they just made up an excuse here that this is that it's a second order relativistic effect. That is not true at all. So when you get into the first order and second order of effects and measurement, right? If you can introduce a variable and there's a directly proportional relationship to what's being measured to that variable that you introduce, and that's a first order effect of it. So what they're saying there, or so what's actually happening is like velocity is a first order effect that will affect the speed of light. It's not a second order relativistic effect. That's insane that they thought that.
You mean the time was different than it should have been? That's not a measurement. That's a computation. We're just going to correct it and delete it.
Yeah, and then tell everyone that C equals C. So that's it for old Wolf and Petty. If
Is that
anyone
the
has
same
any-
Don Pettit that's a astronaut?
No.
I'd like to think so. Like I don't even want to look into it because I don't want
You
to know. Like I like the idea that there's a possibility that that's your boy Don Petty.
He just seems way too not. I don't know. You think he's that smart?
I don't know. Couldn't tell you. I don't really watch much Petty.
Well, no, if you think about it though, right? He did the experiment, he got the data, he's like, "Oh, look it. C's definitely constant. I'm gonna go join NASA."
This was the catalyst for him becoming an astronaut.
Exactly.
He was like, oh my god, relativity is true.
Exactly.
This is so cool.
Yeah, that's pretty much what happened. So, all right. Well, if there's no questions, comments, or concerns, I think we'll wrap it up.
Yeah, we can open it up for a second first here. Just if does anyone have any questions, comments, concerns, thoughts?
I think after watching this presentation, I'm going to immediately go sign myself up for space camp.
I went to space camp.
JK. Yeah, good job, dude.
Cool. All right, well, let's go ahead and wrap it up then.
All
Thanks
right, all right.
everyone for tuning in.
Oh, real quick.
Hopefully,
Sorry,
Yeah.
before I don't want to forget because I'll forget. So on Thursday at 9 p.m., Toby and I are going to go over to Medicinal Mass Media, and we're hosting an event. So everyone's obviously welcome to come. It's going to be like an open Q&A on all the interferometry and ether research that we've been doing. So what we plan to do is kind of go over some of the fundamentals of, what is the ether? How are they referencing it in these papers? Did they fail to measure it? Did they fail to measure the Earth? Like is it a null? Like what's going on? What does it mean? So we kind of want to just put everything forward that we've uncovered and, and what's led us to our conclusions about the measurements that were made and how they and our interpretation of them and why we think what we think. So it should be really fun. We should have some some good questions and some good pushback, some good feedback, and we'll just walk through it all and see what happens. So we'll be restreaming it, but if you guys want to come to the Discord and all that, it'll be links will be provided. So check that out on Thursday.
heck yeah. Thanks everybody for tuning in. And yeah, if anyone ever has questions about any of this stuff, or if you want any of the papers, you want the resources, I mean, I think we've already said this 100 million times, but maybe I'm just feeling like I need to say it again because people have been gaslighting me so much and saying things about how we don't provide sources and this and that. It's funny. I guess if you listened to me last week, I probably sound a little bit different than I do this week because I went through that stupid debate and all those globers. But we always share our resources, and maybe I'm going to start being a lot more forward about it and explicit about it and kind of annoying about it even because, that's just the way we're going to have to be. And I'm going to, if I'm going to do a debate or something, if you want my sources beforehand, talk to me. I'm going to try and make an effort from now on to put things forward before I even do these debates because that's how these discussions should go. And, I may end up in a couple more silly like mudslinging debates here, but I want to try and move towards having more edifying discussions. If you listen to that debate Saturday, I apologize that you had to listen to people scream and interrupt each other in poor moderation. And I hope that we can find some more even keeled venues in the future to do that. But yeah, thanks for tuning in and take care, everybody.